Come on in, everybody. Come on in. Anybody have any questions before we get started? Anything about any past homework, past topics, stuff of that sort?
I have a question about one of the questions from the test.
Okay.
So it's the one about the ball being dropped from above a window.
Uh-huh.
And then it's just like how to find out like the height of where it was dropped from. And I couldn't figure that out.
Okay. Yeah, I remember doing one like this. I might even work one like this on one of my YouTube channels, one of my YouTube videos. Do you have any of the data, the specific data on you?
Yes.
Okay.
The window is 2 meters in height.
Okay.
As it falls, it's visible to a person looking through the window for 200 milliseconds as it passes by the 2 meters of the window. And then it says from what height above the top of the window was the ball dropped?
Okay. And you're saying it took 2 milliseconds to go by it. Is that right?
200.
200 milliseconds. And they're just asking for how high above the top of the window the actual ball was, right?
Yeah.
Okay, so what we can do with this one, I'm gonna try to share my screen. Let's see how that works. And say share screen. Let me let this person in. Share screen. Do share. Now, hopefully, it will just let me. Nope, it's just going to turn right off. Hopefully, it'll let me. Looks like it is. Nope, of course it's not. That's super helpful. All right, so now I got to turn off my Wi-Fi on my iPad and then try again. So what I'm going to do is swipe to open, do this, turn off my Wi-Fi, turn my Wi-Fi back on. We've got some more people coming in, so it's giving us more time. I guess that's a good thing. I'll look at it that way. And now I'm going to say share screen. Hopefully it'll work this time. Pull this down. Still nothing on this one. Still not working. That's not good at all. Try it again. I'm still not able to connect to that. All right, so let me try this. I literally come late because every day I'm testing it, and of course it didn't work this time. So, all right, I got this on. I'm going to go ahead and try to turn on the Wi-Fi here. Connecting. Well, this is good. It's actually asking me for my password for my Wi-Fi. Kind of bothers me that it didn't already know that, but here we are. Okay, so maybe something happens. Okay, it's actually on this time. Maybe that was the problem. Let's see, share screen. Okay, there you go. So I've got a rough drawing, obviously, of the problem. Basically, I'm representing the building or the window as this hole right here to here, and then the rest of the building from which the thing was dropped as just that little height above it. Now, there's equations we can use, but the one that I find kind of useful sometimes is basically that you can find the average velocity a couple different ways. So, for instance, we know that v is equal to v0 squared plus 2a x minus x0 is an equation. Actually, it's v squared is an equation that it's not a vector equation. And as I told you, some instructors don't even allow people to use, but sometimes I like to use that one. And the other one is that the average velocity, and both of these are only true for constant acceleration, is v1 plus v2 over 2. So if I imagine right here, we have v0 equals 0, and then right here we have v equals v1, and then right here we have v equals v2. I might be able to make use of this. So for instance, I know that the average velocity going past the window is v1 plus v2 over 2. And that, of course, has got to equal 2.00 meters divided by 200 times 10 to the negative third seconds, because the other formula for average velocity is x minus x0 over delta t, right? So basically it went a distance equal to the height of the window in a time of 2 times 10 to the negative third seconds. So if I put that 10 to the negative third up at the top, it becomes 10 to the positive third. And I get, in fact, 2000 divided by 200. And that, of course, gives me 10 meters per second. So that's what the average velocity is. So I now know that v1 plus v2 is equal to 20 meters per second. And I also know that v0 plus v1 over 2 has got to equal, well, actually, no, I don't know that one. Hold on. So I know that, but I know also that v1 squared is equal to v0 squared plus 2a times, in this case, I'm just going to say h minus 0. And of course, v1 would be the velocity at v1. So I would say v1 is equal to the square root of 2 times 9.80 meters per second times h, like this. That's v1. And then, of course, v2, I could either put that in terms of v1 or I could put that in terms of v0. But in this case, I want to say, let's see, v1. So that's v1 squared plus 2a times, in this case, it's just, let's call this x for the height of the window, So that's just x there. So that's another way we can find something. Now I'm looking for really just the h. So what I know is v1 plus v2 equals 20 meters per second. If I got v1, then I can immediately figure out what h is. So taking this equation, I'll say v1 squared is equal to 2 times 9.80 meters per second times h. So if I can figure out v1 squared, I can actually get what h is. And similarly, I should be able to figure out V1 plus V2 equals 20 meters per second. That should allow me to find a relationship between V1 and V2. I could also use, instead of V2 squared equals V1, I could do V2 squared equals V0 squared plus 2a x plus h. And I think that might be the better choice. So I'll say V2 squared is equal to, since this is just 0, which is the same thing that happened there, this is just 2 times 9.80 meters per second times x plus h. So I now have an expression for V1 squared, an expression for V2 squared. So I might be able to do something with that. And let's see here. No, I don't see anything jumping out at me that way. If I did V1 plus V2 squared, I had a V1, V2 in there, that would be problematic. I think this is the way I did it last time, and it worked out pretty well. So let's try plugging this in. I'm going to say square root of 2 times 9.80. I'm going to leave off the units right now, times h, plus 2 times 9.80 times h plus x, which the x we know, is equal to 20 meters per second. I said I was going to leave the units off, but I ended up not doing it there. Okay, so I've got that. Now, if I square both sides, I could get, got another student coming in. If I square both sides, I could get 400 meters squared per second squared. And this would become 2 times 9.80 times h plus 2 times 9.80 times h plus x plus 2 times the square root of 2 times 2 times 9.80 squared times h plus x. And all of that would be under the square root. Okay. So that doesn't seem to be jumping out at me. I tell you what, let me look, just because I'm using so much time. This should pan out, but it's not jumping out at me right now. So what I'll do is I'll prepare something for you and either send it out as a text document or create a video and post it online. I don't know. In fact, I might already have it solved up there. Let me double check, see if I haven't already. I just, like I said, I'd hate to waste a whole lot of time doing one particular problem, especially when I got a couple students that still haven't taken the test. But let me see what I did here. Introduction to kinematics. I'm trying to look for some of the most recent videos I made. No, waves. No, these aren't the ones. It could actually be in this kinematics one, but I think that was, yeah, that was recently. No, it would have been the summer or the fall or the spring that I did it. So I guess I might not. Well, I will work out something for it. Who was this that asked us? Which student was it? Was it Jamie?
Yes.
Okay, I will work on that for you, Jamie. I don't know what I'm missing here. I was trying to avoid time because that would be a problem, but and I think what I was doing was remembering a way that I worked before that was really cute and quick. Like I got it in 3 lines, but now I'm not getting it in 3 lines. So whatever cute, quick trick I came up with last time, I'm forgetting right now. So I'll think about it a little bit, and I might even think about it while we're actually doing class. And by the end of the class, I might have it solved. But for right now, I will say, check back with me. I apologize for not being ready to field that right now. Back with me. Yeah, that should work, but it just looks like a holy mess. So I don't think I want that. H squared plus hx. No, that's not it. Yeah, I've done something stupid. I know using this this expression right here, I know that was a neat trick that I pulled last time and it worked really well, but I'm thinking I probably shouldn't have used this. I probably should have used maybe V equals V0 plus AT. That might have helped me. Yeah, that's what it was. Yeah, I could say V equals V0 plus AT, and that would relate V1 and V2 because I actually know A and I know T for it crossing the window. So that's probably what I need to do. So I might actually work that again towards the end of class, and hopefully that'll help. Sorry, I couldn't do that in real time there for you, Jamie. Anybody else have any question I can miserably fail on helping with? I apologize for that. That was ugly. Anyone? Okay, I'll quickly show you that at the end of class, Jamie. If you got a couple minutes, if you got to rush to lab, that's okay. It's not a big deal. What I'll probably do is put it on the end of the video anyways. Okay, so it'll be on the end of the video, whether you guys stick around or not. All right, anybody else? All right, so I didn't want to waste too much time, and I say I'm wasting. It's not really wasting. It's just lack of a better word. I didn't want to use too much time doing that. I really need to get into the idea of adding vectors for you guys. So I'm going to use as my archetypal example of a vector is, well, there's two of them. One is the idea that you can use arrows that you draw on paper or whatever. You can use those as perfect models of vectors. Another one is really imagine your bed or imagine your front steps as the coordinate origin of your life. And then imagine on a given day, you have this little arrow that leaves that origin. In other words, starts at the origin and sits on you all day. So as you make various trips, maybe you walk east from your bed and then south to your door, and then let's say north down the hall or something like that. That little arrow is going to follow you. And in fact, each of those little trips add up to give the latest displacement. Okay, that's what that vector is called, is your displacement vector. And when I use the word vector, I've hinted to you before that vector starts with a V, just like the word velocity starts with a V. And that scalar starts with an S, just like the word speed starts with an S. And those are both really good clues to help you remember, are really good, memory devices to help you remember that vectors, a velocity is a vector quantity, and that speed is a scalar quantity. And the difference between a vector and scalar can be gotten just basically from watching Despicable Me, where the bad guy in that was a guy by the name of Vector. And he said it was a mathematical term, but he was saying because he does evil with direction and magnitude, that was why he chose the name vector. And that's actually it. A vector is a quantity with magnitude and direction, whereas speed is just like something with a magnitude. Okay, if you look at your speedometer, it says, maybe 60 miles per hour. That doesn't give you any direction, so clearly that's a scalar. However, if you have, say, a dash mounted compass that lets you know your compass heading, HEADING, then you could look at that in combination with your speedometer and conclude that you're going 60 miles per hour at, say, 10 degrees east of north. When you do that, you're now telling me, or you're now having a velociometer, and you're able to tell me your vector velocity. So that's a nice example to think of. So if you want to think about how to add vectors and stuff like that, we'll think of multiple trips, the trip east by 3 meters from your bed, and then the trip south by 4 meters to the hallway. Each of those are individual trips. At the end of those two trips, the sum of the first trip and the second trip is the vector displacement at the end. So that gives you a natural way to add vectors. But in order to do that, I need to give you some idea about vectors in general. So first off, I'm going to tell you how we specify vectors. So vectors are specified, at least with handwriting. You normally write a capital letter and you write an arrow over top of it. Textbooks normally will use just a bold print capital letter, and that will represent a vector. But some books actually take the time to draw little vectors over it.
So I'm going to say, let's imagine the typical situation where we have a vertical y-axis and a x-axis pointing to the right. Okay, that's a very typical scenario. And if you don't draw one, we often assume that's the case, but I recommend you don't do it that way. In reality, you pretty much need to always draw a coordinate system so anybody grading your test or whatever will know what you're talking about. Now, we might make a scale of, let's say, 1.0 centimeters equals 10.0 newtons. And this 10 centimeters is something that you'd measure on paper. Okay, that's a typical scale. But once you make that scale, you now have a set scale that you can use, and you can convert back and forth to numbers on the paper versus reality. Okay, in other words, you can treat that just like a conversion factor. It could be 10 newtons over 1 centimeter, or it could be 1 centimeter over 10 newtons, depending on which number you have and which number you want. So I might represent this vector right here. Let's pretend I took the time to actually measure it correctly. And I'm going to call this vector A, like this. And I'm going to say the magnitude of the vector. Notice if you have the vector symbol A with an arrow over it, you can refer to its magnitude by putting absolute value bars around it. And I'm going to say that's 250 decimal point 0 newtons. Now, what I'm pretending I did there was I took the time to actually measure this and found out that this distance was 25 centimeters. Okay. And not only that, I took a protractor and measured that to be 50.0 degrees. Okay. So if I actually did this with a protractor and actually measured this on a piece of paper and decided to measure out 25 centimeters at 50 degrees, I'd literally lay my protractor with the origin at the center of the circle of the protractor. I would make a mark out at 50 degrees as far from the origin as I could, and then draw a line from the origin through that mark, and then erase it until it got exactly 25 centimeters, because 25 centimeters, of course, corresponds to 250 newtons. If you did all that by scale, and then, of course, if you had to add another vector, you could put another little coordinate system at the head of this one and do it all over again. And you can do that with any number of them. You can actually add vectors that way. You just have to know, how do I put them, how do I orient them, and then how do I measure the final result? In other words, you measure a certain number of centimeters and use that to convert to newtons. You measure a certain angle, and that angle will be right on the money. And that should give you a result graphically that's within a few percent of the actual answer that you get if you did it mathematically. Okay. So how do I specify a vector? Well, I'm going to say the vector A, and this is a very typical way of saying it, is equal to 250 decimal point newtons at 50.0 degrees. Now, when I specify just at, and I don't say anything about it, then physics instructors and math teachers go on the assumption, ideally it's not assumed that the x-axis is pointing to the right and the y-axis is pointing up. But if you didn't draw that, that's sort of what they're leaning towards thinking, but it'd still be better to draw x-axis pointing to the right and y-axis pointing up. But this at positive 50 degrees suggests that I'm going to measure the angle counterclockwise from the positive x-axis. And that's exactly what I've done here. So this being positive means counterclockwise from positive x-axis. That's just the nature of it. You have learned that in your trig class or in your pre-calculus class, and that's what it is. If it happened to be a negative angle, then it would be clockwise from the positive x-axis. But it turns out by default that another way of writing this is to realize that your axes can also be this is X, but it's also north, or excuse me, that's not X. This is Y, but it's also north. And this is X, but it's also east. And this would be south, and this would be west. In which case, this vector could also be specified as 250.0, or actually not 0.0, 250 point newtons. And this time we'd say it is at 50.0 degrees, and we'd say north of east. Okay, that's another way. See that I'm actually going up from the positive x-axis, and the positive x-axis is in the east direction. So north of east would be exactly what we have. Another thing we can say is that north corresponds to 0 degrees, and then east corresponds to 90 degrees, and south to 180 degrees, and west to 270 degrees. Okay. So we could also, ignoring that red for a second, I want to show you one other thing that it can do, or it can be, is I could also call this 250 newtons at 40.0 degrees east of north. So that's acceptable as well, because obviously if you go up counterclockwise from the positive x-axis 50 degrees, that's the same thing as going to the right, which is eastward from the vertical axis 40 degrees, because the sum of them equals 90. Does that make sense to everyone? So that's another way we can actually specify a vector's magnitude and direction. But there's other ways, and in fact, to make sense of those other ways, I need to teach you a few more things about vectors. So let's imagine we have a vector A. And what I want to do is imagine you walk the distance A. Let's say you walk 30 meters north and then 40 meters east. So you might actually say, I walk 30 meters north, which looks like this. Whoa. Which looks like this. And then you walk 40 meters east. Okay. Now this looks like this. And in fact, your resultant of that vector is this vector right here. And let's say that's the vector A. Okay. Now that gives you some idea of how vectors add. When you have two vectors head to tail, notice the head of the 30 meter vector, the arrow part, is touching the tail, the stick part of the 40 meter vector. When you have vectors like that, you can actually put them in any order, because it'll turn out that A plus B is the same as B plus A. You can put them head to tail, head to tail, head to tail forever, and just draw from the first tail to the last head, and that will be your sum of your vectors. So A is equal to, let's say this is our n vector, at least its magnitude, and this is our E vector, again, at least its magnitude. So this is n plus E, which, by the way, also happens to equal E plus n. Now, if I told you you walked twice as far, or you took double the trip, I think you would probably interpret that as maybe the equivalent of walking 60 meters north and 80 meters east. And in fact, the magnitude of this E for this particular case, or this A vector, is actually equal to 50 meters. So in fact, you'd walk the equivalent of 100 meters. Does that make sense to everybody? Do y'all agree that if I walk twice as big a trip as A, I would be equivalent to going 60 meters north, 80 meters east, and or just 50 meters, or excuse me, 100 meters at that diagonal? Does that make sense to everyone?
Yes.
Okay. So what I'm going to say with that is I am going to compel you to think that in fact, there's a vector, let's call it 2A, that will actually equal this. So in fact, if you multiply a vector by a scalar, if the scalar is bigger than 1, you're just going to change its magnitude and make it bigger. And in fact, this magnitude would be twice as big as A. If you multiply a scalar that is less than 1 by a vector A, then you're going to get a smaller vector. So for instance, you might actually get something along the lines of this for 1/2 of A. So this would be 1/2 A. Does that make sense to everyone? So we're just reasoning on the idea that a typical vector would be a line pointing from where you were to where you ended up after taking a walk. Now that walk could have been straight along that diagonal, or that walk could have been first you going north and then you going east, or that walk could have been first you going east, then you going north, but all three of those results would end up in the same vector A. Does that make sense? Okay. So now, yeah, thank you for that. Now that we have that as a plan, we want to think about what happens when I do the opposite. So if I told you I walked 30 meters north, what would be the opposite of walking 30 meters north?
$30 meters south.
Exactly. And that's exactly what we need you to think about. So if I were to say, draw the vector negative A, then what I would do is draw this vector, and that would be negative A. So basically I've done the equivalent of putting the arrow at the opposite side. And the reason why I use the word opposite is because in algebra, remember we learned and defined, like when we were learning how to add and subtract positive and negative numbers, we found that A minus B was defined to be A plus the opposite of B. So that was some very distinct wording. And in fact, that is one of the rules of algebra. There's other ones like the distributive property, the commutative property, the associative property, stuff like that. And those particular properties are actually not just rules to help you solve an equation, which is normally the way you learn them. In fact, an algebra is a thing. It's a set of operations that create only things that are within their set as well. And there's different types of algebra. There's Lie algebras, there's spinor algebras, there's matrix algebras, there's vector algebra, there's regular algebra that you're used to dealing with. And when you learn more advanced mathematics, you'll understand that. But those rules that seemed kind of stupid and not necessary were really the only things that make it behave the way it does. So this A minus B is defined to be A plus the negative of B is a rule for algebras. And in fact, it's going to come in handy when we go to learn how to subtract vectors. Okay. So now I've got an idea of what negative A is. I think you can probably guess what negative 2A would look like. Anyone?
Negative 60.
Yeah, exactly like that. It would be in the opposite direction, but it would also be, of course, twice as long as A. So there's an example of negative 2A. Okay. So we're learning now what happens when you multiply a vector by a scalar, and that's going to come in handy because it turns out you can create a coordinate system like this. Let's say And this is kind of weird, but it turns out when you do this, your coordinate system has to be a right-handed coordinate system. Well, I don't know why I wrote that last one. A right-handed coordinate system. And what that means is, if everybody look at me a second, if you hold your right hand like this, sort of like you're holding a gun, you know, like let's say your middle finger is your trigger finger, which is weird, obviously, but let's say you're putting your right finger along the barrel, say, of the pistol. And I don't know why I went with gun, but here I am. And so anyways, so you put your index finger along the barrel, which is a surefire way to get your finger broke. Okay. You're sticking your right middle finger in the trigger hole, which is a really dumb way to shoot. And what's worse is you're going to get your thumb broke off because you're sticking your thumb up behind the rack that's going to slide back and break your thumb. But anyways, let's imagine doing that. When you do that with your right hand, your index finger can represent the x-axis, your middle finger can represent the y-axis, and then your thumb has to represent the positive z-axis. If that's consistent with your drawing, as mine is here, then you know that you've got a right-handed coordinate system. So mine has the x pointing out of the screen. So that's like that. It's got the y pointing to the left, and it's got the z pointing up. So you can clearly see that mine's a right-handed coordinate system. The deal is, if you don't have a right-handed coordinate system, cross products and determinants and things like that can actually be off. So it's just best to always use a right-handed coordinate system. Now that I've got that out of the way, I'm going to tell you there exist these little vectors that people have made up for our convenience because they're just so kind. And those little vectors are unit vectors. Whoa. Those little vectors are unit vectors. Okay, my automatic making things awesome is not working, so I'm going to say bump that. So I'm going to say there's this vector right here, which is literally 1 unit long. Okay. And when I say unit, I'm not talking about a meter. I'm not talking about a Newton. I'm talking about 1 unit, period. Okay. So this vector is called I hat. And that hat, that little sort of greater than symbol on its alligator mouth or whatever, that actually means a unit vector. Now, sometimes people choose to use X hat, and that's certainly fine as well. Okay. Then they define another one that's also a unit vector. And in that case, that vector is called J hat or Y hat. And sometimes people will use capital X and capital Y instead of lowercase x and lowercase y. And then finally, there's a third one here. And I say finally, but there's actually ones for other coordinate systems too. And this one is K hat, comma, Z hat. Okay. So now, if you think about vectors this way, if you think of these vectors existing and being 1 unit long, if you needed a vector pointed in the x direction to have a length of 3, all you have to do is multiply 3 by I hat. Let's say a length of 3 meters, you multiply 3 meters times I hat. So that's all you really have to do. Does that make sense to everyone? Similarly, if you had a vector pointing in the y direction that was 14 newtons long, you just multiply 14 newtons times J hat and you're golden. So that's going to give me another way to express these this vector A that I defined at the beginning. So let me do that with a little bit of trigonometry. So what I see here is I have a vector A whose magnitude is 250 newtons. And I know this angle right here is 50.0 degrees. Now, if you imagine a laser that shot vertically downward, in other words, parallel to those vertical lines, then, and I move it from left to right, from negative infinity all the way to positive infinity, what's going to happen is I'm going to get a shadow down here of the vector A. And that shadow is what we call the x component because it's parallel to the x-axis. It's the x component of the vector A, which as a vector, I can write it AX with a vector symbol. Similarly, if I imagine there's a piece of plywood vertically leaning against the tip of A and AX, and then I use a laser that shoots horizontally, then a shadow will be produced right along here. And that is in fact the vector AY. Again, it's a vector because I took the time to write the line segment with the little head on it. Okay, now, when you first draw a vector like this and you're trying to break it down in components, that's what we're doing here, is we're breaking it down in components. What I want you guys to do is not be ashamed of taking your time. In other words, we always use sine and cosine if we have the length of a vector to find the X component and the Y component. And students often make careless mistakes in trying to find whether the sine makes the X component or the Y component. So what I recommend you do, at least for weeks, is go ahead, as soon as you have a vector in the XY coordinate system, I want you to go ahead and write down what the sine of the angle is and what the cosine of the angle is, and then that'll keep you from making a mistake. So I'm going to write down that the sine of 50.0 degrees, and remember, I use the mnemonics, some old horse came hopping through our alley. So some old horse's sine equals opposite over hypotenuse. And the angle that we're talking about is this 50. The opposite angle is, or excuse me, the opposite side is the side that it's not touching. And remember, the right angle for a right triangle acts like an arrow that points to the hypotenuse. So the A equals 250 newtons is in fact the hypotenuse. So it can't be opposite or adjacent. So you know, in fact, that sine is AY. Notice I just wrote magnitude now, over 250 point newtons. Okay, sorry about that. Now I'm going to take the right time to write cosine. Came a hopping is what cosine is. So that means cosine equals adjacent over hypotenuse, and adjacent side is the side touching the angle. So you see that is in fact AX over 250 decimal point newtons. Now you will find out a lot of times cosine gives you X and sine gives you Y, but it's not always the case, because I always want you guys, one, to never, ever, ever put a negative into a trig function or an inverse trig function. There's ways to do that. And if you're really savvy and pay close attention to the rules of trigonometry, you can pull it off and not make mistakes, but it's just not worth it. It's much more physical to go ahead and just assign the signs yourself. And that's what I want you guys to do. So when you have a vector and it's sitting there in one of the quadrants of the XY coordinate system, I want you to find one of the angles, whether it's the one from the vector to the x-axis or if it's the one from the vector to the y-axis, doesn't matter. You just then use your understanding of sine as opposite over hypotenuse and cosine as adjacent over hypotenuse to figure out what's what. So when I do this now, I can now say that AX is equal to 250 newtons times cosine 50.0 degrees, and it's going to be positive because it's to the right. That's where I'm forcing the sine to be what I need it to be. Okay, that's important that you take the time to do that. So I'm going to take 250 and I'm going to multiply it times the cosine of 50. So 250 times trig cosine 50. I'm making sure I'm in degrees, and I get 160.7. That's one extra sig fig, 160.7 newtons. And I'll underline that to represent the fact that it's one extra sig fig. Now I'm going to say well, I don't know why my thing keeps switching to an eraser, but it does, and that's kind of aggravating. And I also don't know why this happened, but I'm going to go back and fix it now. Okay, so now I'm going to write AY is equal to 250 point newtons times the sine of 50.0 degrees. And again, that one points up. So what I'm doing to think about whether the component is positive or negative is I start at the tail of the vector right here, and I imagine walking either first parallel to the x-axis and then second parallel to the y-axis, or I can do it the other way. The main thing is I just do it parallel to the x's and y's axes, and I do it such that I end up over here. Okay. Well, when I do that along the x-axis, it's clear that I'm going to the right, which is the positive direction. So the x-axis is a positive component. Similarly, when I go along the y-axis, I'm going in the up direction, which is again positive. So again, that one's going to be positive. So that's what's actually going on here. So this is 250 times trig function sine 50. And this one gives me 191.5. So I'm going to say positive 190. I don't know why it keeps positive 190.5 newtons, again with one extra sig vig. Okay, so now I have my components of the vector A. So that gives me yet another way to write my vector A. I can say my vector A is 160.7 newtons I hat plus 190.5 newtons J hat. Now I could also put parentheses around the whole thing and just leave the units off until the very end, and that would be acceptable as well. In other words, put parentheses around the 160.7 I hat plus 190.5 J hat, and then close parentheses and put newtons after it. That would be acceptable. I could also write 160.7 X hat plus 190.5 Y hat, put parentheses around it and say newtons there. That's acceptable. And I could actually save some time and use this nomenclature. You guys know that when we talk about points in space, we'll say X, comma, Y, comma, Z in parentheses. Well, you can specify a vector like that too, but we normally, instead of using parentheses, we actually use less than and greater than symbols. So I could avoid writing the I hat, the J hat, and the K hat, or the X hat, Y hat, and Z hat, and just write 160.7 newtons, comma, 190.5 newtons, and just write it like that. Of course, this one doesn't have a Z component, but I could put comma 0 and then do the greater than symbol. But all of those are perfectly fine. Now, what you have to watch for is when a homework system or a teacher or a test asks for you to add vectors or something like that, they might ask for you to give the vector in a very specific notation. They might ask for magnitude and direction notation, which is what that first part was. Or they might say how many degrees north of east, which again is that second version. Or they might say a certain number of degrees east of north, then you got to flip it and make it 40. Or they might ask you to report it in IJK notation. Or here's another one I haven't written yet, but we could also say it is 250 newtons at compass heading Notice the compass heading starts at 0 and goes clockwise around the axis, reaching 90 degrees when it's east and 180 when it's south, so on and so forth. So this one I have to go down to 40. So I say compass heading 40 degrees. So that's yet another way to write that. Now, if you look at the link I gave you on your weekly module for this week, you'll see there's one link to my YouTube channel that says the world's greatest vector addition problem. It is not necessarily that great. The key is I sort of made sure I covered every possible way of specifying a vector, just like I did right here with you with those 1, 2, 3, 4, 5, 6, 7 different ways I specified that one vector. I use each of those ways in that problem to specify a certain number of vectors, and then I add them all. So I'm showing you how to add vectors. I'm working out whether the components are positive or negative, which again is another skill you need, and all that. So it's really a good problem to work. What I recommend you doing is watching that video in its entirety, making sure you follow it. If it gets too boring, pause it for a little bit, take a break, come back, watch it again, start it over again. But when you're all done, come back, turn the video on, record the actual vectors that I'm asking you to add, and then try to do it yourself. Try to do it graphically, which all you have to do is you draw the first vector with its tail at the origin, choose a scale. Obviously, you want to probably start at the bottom left-hand corner of a piece of graph paper for best results. It could be just notebook paper, but graph paper works better. And maybe even in the middle of the bottom of the page. And you want to make the scale as big as you can, but not so big that you can't fit it in the paper. So you make up that scale, you use your protractor, you put the vector, then at the head of that vector, you draw another coordinate system where the X and Y axes are parallel to the original. And again, you use the scale to choose the size, and you use a protractor to choose the direction. And then at the end of that, the head of that vector, you put yet another axis, and you keep on doing that until you've accounted for all the vectors. When you're done, you just connect the tail of the first vector to the head of the last vector and put an arrow on the head end. That's the sum, or what we call resultant, and we normally indicate it with an R, of those vectors. Now you can measure that vector in centimeters and convert that to newtons if you want, and that'll give you the magnitude. Then you can actually measure the angle to the nearest axis and label it, of course, use the inverse tangent to compute that, or actually use a protractor to measure that, excuse me. And then you can say, that's its direction. Maybe you measure 15 degrees to the left side of the y-axis. So you can call that 15 degrees counterclockwise from positive y-axis. Or you could call it 15 degrees west of north. Or you could call it 75 degrees north of west. Or you could call it, since 360 is north again, you could call it 345 compass heading. Or you could call it 105 degrees because it's just measured out 90 plus 15. So there's all different ways you can do it. And in fact, that graphical method should give you, like I said, within 5% of the actual method. Then you can go back and try to add it by using trigonometry and mathematics. Okay, so you can actually add vectors with no math. You just have to, use geometry and that sort of idea. But you can also now add it with math, and hopefully you'll get the same answer. If you don't, you're probably not understanding something, or you might have found an error in my problem. I don't think there's any errors in it. I set it up so it should be done properly. I did it like 3 times to make sure it was error proof, but I'm sure it still has a possibility of having an error in there. So does everybody understand what we've done so far with these vectors? Okay, so the deal with this is sort of just getting us started. What I want you to be able to do, though, is I need you to be able to understand graphically how vectors are combined. So let me say, for instance, I have a vector A and a vector B that are tail to tail. And I want to know R, which equals A plus B, is equal to question mark. Well, I told you vectors have 2 things associated with it. What are those 2 things?
Magnitude and direction.
Exactly. So at least right now, you can do anything you want with a vector as long as you don't screw up the magnitude. In other words, you don't want to stretch it or compress it, and you don't want to twist it, because then you change the magnitude or the direction, right? So you can imagine this A axis, for instance, as if it is able to be slid along, and I will take and slide it down and to the right, and then the A axis, or the A vector, will appear right here. Similarly, I can imagine the B axis sliding along, or the B vector sliding along A, and I'll get that there. Well, now if you look, you've got B plus A, because remember the displacement vector was basically if you walked east one direction and then north a direction, then the sum of those two was aligned from the very beginning, the tail of the north vector or the east vector to the head of the north vector. So we know how to add them once they're head to tail. So now I'm going to do is say that the vector goes from the tail to the head. In other words, they started off at the common tail and ended up on the common head. So this is the vector R. So that's how you add two vectors when they're tail to tail. So tail to tail, add implies complete the parallelogram and R is from common tail to common head. Okay. Now, what if we had two vectors head to tail? So I have vector A, say, and then I have vector B like that. Well, this is just like you walked on the trip A from your bed, and then you hung a right and walked on the trip B from there. So obviously, the sum of these two guys must go from where you started to where you ended up, and that is R, which is equal to A plus B. Okay, so head to tail, you just add by going from tail of first to head of last. So that actually covers for any number of vectors, not just two. And you can do them in any order. Okay, so if you had vectors A, B, C, D, E, F, G, you could write them A, and then at the head of A, you write B, and then at the head of B, you write C, and so on and so forth. But you could also write them A, E, F, C, D, and it would still give you the right answer. Okay, now let's consider subtraction. So A minus B is defined to be A plus the opposite of B, just like we learned in algebra. Okay. So now what I'm going to do is draw two vectors tail to tail. Right. So let's say my vectors are A and B. Okay. So the first thing I want to do is I want to realize that A minus B is the same thing as taking A and negative B and adding them. So what does negative B look like compared to B? Is it perpendicular to B? Is it parallel to B? Is it anti-parallel to B?
Be anti, right?
Yeah, it's anti-parallel. And in fact, I just drew it in blue. So I'm writing negative b next to that in blue. And I think you can see now the blue vector is head to tail with the A vector. So you can say, in fact, that A minus B is that vector right there. So subtracting these two, what that means is reverse. Whoa, here it goes again. Reverse B to make negative B, and then A and negative B are head to tail. So you draw from tail of B, of negative B technically, to head of A. Does that make sense to everyone? Now let's try head to tail. So if I had A right here, and I had B right here, when you're subtracting, it's not going to be quite nice like it is when you're adding. When you're adding, head to tail is a godsend, but when you're subtracting, it's horrible. So again, I have to write negative B. So I'm going to say this vector right here is in fact negative B. Everybody agree with that? So now I can slide negative B along here until I get negative B like that. And if it helps, I can also slide A over here like this. But now you can see I've got negative B and A in the head to tail orientation. So this is A minus B. So subtracting, I reverse B to make negative B, and then complete the parallelogram. There, well, that looks horrible. There will be a comma negative B configuration in head to tail form. So A minus B goes from tail to head. That makes sense? All right, so that's pretty much all the details of adding vectors and all that good stuff. I will tell you that if you're actually doing this algebraically, what you're going to do is like I did with vector A, I found the X component and I found the Y component, and I made sure they had the right signs. Then I add up all the X components for all the individual vectors and get a new X component for the resultant. Then I do the same thing for all the Y components and get a new Y vector that's the resultant Y component. If there's a Z axis or a Z component, you got to do the same thing there. Now, when you're finished with all that, you need to possibly express the vector like I did initially, which is in magnitude and direction form. So if we actually had to do that, we would then take time. Let's pretend like I actually added all that. Pretend I added all of the X components to get R equals, or R sub X equals 28 newtons. And I added all of the Y components to get R sub Y equals negative 32 newtons. Okay. So then what I'm going to do is I am going to draw a coordinate system. There's my X. There's my Y. My R axis is 28 newtons. So I'm going to say and my RY is 32 newtons in the negative direction. So I'm going to make sure that's a little bit bigger like that. And then I'm going to realize that, in fact, my R resultant is from the tail of that to the head of the next one. So that's the vector R. And I'm going to call this angle theta or phi or alpha or whatever. But there's the angle theta. So I can now say that R's magnitude is the square root of 28 newtons squared plus 32 newtons squared. And that gives me $45.5 newtons with one extra sig fig, of course. Okay, like I've been doing. That also tells us that theta would be equal to the inverse tangent of 32 over 28. Notice I did not use any signs. So I'm going to do tangent inverse of 32 divided by 28. And that gives me 48.8 degrees. So I could report R is equal to 45.5 newtons at negative 48.8 newtons, or excuse me, degrees. And that is a acceptable way to report it. Okay. I could also say 48.8 degrees south of east. I could also say 52.2 degree or 42.2 degrees east of south. That would be another option, so on and so forth. But that's the final part of the adding of vectors. You just have to do that. Now we've only got 10 minutes left. I want to cover a little bit. Does anybody have any questions about any of this before I give you my little quick and dirty spiel on projectile motion? I'm actually going to put your projectile motion back to Wednesday for the concept questions and for the part one, and then I'll put it to say Sunday for the chapter 3, part 2. Okay, so I'm going to give you an extension on that. But anyone have any questions on this vector stuff? Okay, so the main trick with projectile motion, this is really what you need to know, is that we don't handle air resistance. So that means there's only acceleration in the downward y direction, if you're assuming up is the positive y direction. And in fact, the motion's quite separate. There's a nice picture in your textbook of a yellow ball and a red ball, one shot perfectly horizontally at the exact same instant that a red one is dropped from the same height. And in fact, at each time interval, they are exactly the same height. In other words, the horizontal motion and the vertical motion are completely separate. So you can treat a projectile motion problem as you threw a ball up with some initial velocity, and you're going to see how long it stays in the air. And that's going to tell you how long it stays in the air. It tells you how long it has to travel with constant velocity to, say, the right. And that's all projectile motion is. So for instance, if we looked at a coordinate system like this, say, and I assume that I'm landing and launching from the exact same height, which isn't always the case, then I'd say my initial velocity is v0 and it's at some angle theta. Now, when this is fired, it's going to go up, reach some max point and fall down. So ideally, we'd like to know what H max is. We'd like to know the T at the max is. One thing we do know about that is V at the max is equal to just V sub X. In other words, there's no Y component because that's the definition of reaching the highest point. We'd also like to know the T aloft or the T hang time, anyone you want to call that. You might want to know V final, the final velocity. You also want to know the range. How far did it land, which we might call X max. Okay, so those are all things we might want to know. Now, what we know is that V is equal to positive V0 cosine theta I hat plus positive V0 sine theta j hat. So you can actually write a position vector as if it's two motions separately. The y component is just going to be, I'm treating the y as if I shot something vertically upward. So, and I'm saying it started from the origin, so there is no y0. So I'm going to get negative 1/2 g t squared plus v0 t sine theta, all that in front of I hat, and then, or excuse me, all that in front of j hat's what that was supposed to be. And then the other one is just basically, remember the equation, average velocity is x minus x0 over t. Well, in the horizontal direction, the velocity is a constant, so v bar is just equal to v is equal to x minus x0 over t. So x is just x0 plus vt. So in this case, we started x0 equals 0. So I'm just going to get v0 t cosine theta is my I hat direction vector. Okay. If you took the derivative of that, you would, of course, get negative gt plus v0 sine theta j hat plus v0 cosine theta I hat. I'm sorry, I'm writing them in this reverse order. I just had to stick with it. And of course, if you took the derivative of that, you just get negative g in the j hat direction. So all that looks kosher to me. And in fact, you can go ahead and solve in terms of this. Like if I want to know how long it is aloft, or if I want to know how long it takes to get to its max height, then I just got to figure out at what time t the y velocity is 0. So if I look on this velocity equation that I got, it says negative GT V0 sine theta. If I set that equal to 0, that'll give me T max. So I'm going to take negative GT plus V0 sine theta is equal to 0. And this is at max. So that's the T max. So that gives me T max is equal to V0 sine theta over G. Now, this works for any projectile fired from a given height, and then that's ostensibly going to fly over level ground. Can anybody guess from the symmetry of the problem how T aloft or T hang time is related to T max? Anyone?
Ask the question again, please.
Can you anybody tell me how the T aloft, the total time it takes for it to land again, is related to T at the max height?
T aloft would be double T max height.
Excellent. Perfect. That's exactly right. And in fact, we can see that by saying T aloft equals T hang time implies I want Y equals 0. So I look at my R vector. My R vector has a Y of negative 1/2 GT squared plus V0T sine theta. So 0 equals negative 1/2 GT squared plus V0T sine theta. This isn't as bad to solve as you might think. I can factor out a common factor of T, and I get negative 1/2 GT plus V0 sine theta, like that. This means T equals 0, R, and that's what you expect, right? If you fired it at T equals 0, then clearly it's going to have a 0 height at T equals 0. The other one happens by me setting this other factor equal to 0. So I'm going to say 0 equals negative 1/2 GT plus V0 sine theta, which I think you can see T hang time is going to in fact equal 2 V0 sine theta over G, which is exactly what I think it was Jamie predicted. Isn't that awesome? And in fact, when you know that that's how long it's going to be along in the air, you can take that same vector R and say, well, what is my x position at that time? Well, my x position is V0T cosine theta. So I'll say x max is equal to V0 TH cosine theta. So that's going to be V0 times 2 V0 sine theta over G times cosine theta, which there's a nice identity. 2 sine theta cosine theta is actually equal to the sine of 2 theta. So I can finally say that the range x max, again, from firing and landing at exact same height, should be equal to V0 squared sine of 2 theta over G. And in fact, if you graph that, you would see that because it's a sine of 2 theta, it reaches its max there. And unless you have to get the actual max, which is V0 squared over G, then you have two choices of angles, the low trajectory and the high trajectory. Okay, so Shaquille O'Neal tends to use this one on his free throws, or used to. Whereas, let's say, LeBron uses this one. Okay, he's a much better free throw shooter than Shaquille. Just about everybody's better free throw shooter than Shaquille. But that's the low trajectory versus the high trajectory. Now, if you're actually trying to maximize your distance, like you're shooting a full court shot, you're probably going to have to push it with all your might. and then you have to maximize it by using just the right angle, and that angle should be 45 degrees. If you had air resistance, sometimes it works out to be that you have to throw it a little higher than 45. Sometimes it works out so you have to throw it a little lower than 45. But generally, without air resistance, to get the max distance, you should throw it at 45 degrees. Any questions on that? All right, so I'm going to give you those extra days on that homework. Our time is up now, but you actually have everything you need at this point to actually complete all of chapter 3. But like I said, I am going to give you extension on the homeworks. So everybody's free to go. I will wait for the last person to leave before I go. I'm actually going to work that problem that Jamie brought up at the end, but y'all might have to go to lab and all that. So have a good one. Thanks for coming, everybody.
They didn't reschedule the lab from Monday to today, did they?
Oh, no, I'm sorry. I just forgot. Yeah, thank you for that. I just forgot what day of the week it is.
I had a question, Professor.
Yes.
Can you go back to the right-hand coordinate system?
Yes.
How do you annotate vector angles on that? Or is it assuming that that's Z and Y is 90 degrees and X is 135 between the
Okay.
two?
So if you want to talk about that, what I'll do is I'll draw this for you to make some sense of it. So if you're talking 3 dimensions, then there's a couple different ways you can do it. But one typical way is by using, say, spherical coordinates. And what we do then is, let's imagine a point right here, which would have coordinates X, Y, Z, but it also have coordinates R, theta, phi. Okay, what does that mean? Well, if you drop the vertical from here, this distance would be R, this distance would be rho, this angle would be phi. It's called the polar angle. And this angle right here would be theta. Okay, that's in the XY plane. So in fact, you can see R is equal to the square root of X squared plus Y squared plus Z squared. You can say that Z would be equal to R cosine phi. And you could say that X would be would be rho cosine theta, but rho is in fact equal to R sine theta. So sine phi cosine theta. And then Y, of course, would be R sine phi sine theta. So that's how you deal with angles in 3D, or that's a way to deal with angles in 3D. You can use the coordinate system, cylindrical coordinate system, where this is your x-axis, this is your y-axis, and this is your z-axis.
Okay, are we going to cover that later, or is it something?
No, I actually do an intro to that in my YouTube channel. We do use that a little bit in 242, and I treat that as week 0 requirement. So we'll talk about it a little bit more as the semester progresses. But right now, that's really more than what you need to know.
Okay, well, that's good then. Thank you.
No problem. Anybody else have any questions?
Yes. I missed the quiz for this week. Is it possible for me to still pass the class?
You missed the online test?
Yes.
Yeah. I can, anybody that missed it, I can give it to you, give you another week for it, but I'm going to take 10 points off. So no, it's not going to fail you.
Okay.
And I dropped the lowest, so that could be the lowest. But yeah, let's try not to do that anymore. Just send me an email. Let me know your first and last name. Remember, tell me what section you're in, and I'll set it for a whole week. Basically, that usually means till the 11th at 11:59 p.m.
Okay, thank you.
And you still get multiple attempts, so do as well as you can.
Okay, thanks.
No problem.
This is the test that's in Canvas, correct?
Yes, in Canvas.
Okay, thank you.
Module called online tests.
And it's multiple attempts?
Yep, you get 3 attempts and only your highest counts.
Okay, thank you.
No problem. Anyone else?
Have a good night.
All right, you too.
I have another one if no one else does.
Okay, go for it.
Can you go back to the last slide? Where you were moving through things kind of fast.
Yeah, that one.
So when you get to, so I get the derivative, where you, or not the derivative, but where you factor out the t, what, I don't see how you got t height from rearranging that, or did you do something else?
You're talking about on this part right here.
Yeah, so you got, I see you factor the t, and then how do you? Can you
Okay, so this
explain-
is the old adage that the whole reason we learned to factor things was we turned sums and differences into multiplication.
Correct.
So by factoring that t out, I got t times negative 1/2 gt plus v0 sine theta. Those two factors multiply to give you 0, which means either one or the other or both has to be 0.
So you
So
just
if I-
factored out the t, and then you just rewrote the equation without that t.
Exactly, because one option is t is the 0. The other option is this factor equals 0. And that's what that is. So if I set negative 1/2 gt plus v0 sine theta to 0, and then I solve for t, that gave me the actual th that I wanted, which was 2v0 sine theta. It's kind of the bummer about physics. We assume that you've learned everything in math you're supposed to know up to this point, or have supposed to been exposed to at this point, and we expect you to know it 100%.
Yeah, no, I'm in Calc 2 right now. I don't see how you got from the negative, half GT plus V0 sine theta, and then you got a 2 in your numerator for T height.
So first off, I had to take the first term, negative 1/2 GT. I put that on the other side. That becomes 1/2 GT equals V0 sine theta. Then I multiply
Okay,
this.
it makes sense now. I didn't.
No problem.
Yeah.
So that helps you sufficiently.
Yeah, I'm good now. Yeah, I just.
Brain fart. Happens all the time, man.
Is there, so like when you say all of our math, is that through Calc 3 or?
No, okay, that's the other side of the physics and engineering world. Your math is never going to be good enough for your physics and engineering classes. You're always going to be learning your math from your physics instructors and your science instructors and your engineering instructors. Give you a perspective on that. I finally got a chance to take a differential geometry course in grad school, and I'd already had general relativity. And general relativity, like day one, you're doing covariant derivatives, or usually like day 3 or something like that, you're doing covariant derivatives. By the time I finished the 1 semester sequence in differential geometry in the math department, the very last day we got to covariant derivatives.
Okay.
So
I just want to make sure I'm not like screwing myself by in calculus before doing physics.
No, you're actually learning where it'll help your calculus and it'll help your physics. Your calculus will help your physics. So you're learning a little bit beyond what your calculus class is going. I will teach, and in fact, I'll be teaching beyond what your Calc 3 class will even cover, because usually our Calc 3 classes don't get to do vector calculus very much. They might get the generalized chain rule, which involves a gradient and a matrix multiplication, but that's about as far as they get. Whereas we're going to be covering surface integrals, line integrals, curls and divergences and all sorts of stuff. So we're actually going beyond what most Calc 3 courses cover, and we'll do it in calculus-based physics.
All right, thanks. Have a good
No
night.
problem. Don't worry too much. You'll get it. Anyone else?
I had a question about the example on the page before this.
Okay. That one.
So, yeah, that one. So when you were solving for R at the top there, when you did the
Mhm.
square root of 28 squared plus 32 squared,
Mhm.
did I miss something? Because when
Yeah,
I
I just pulled those numbers out of my rear. I was pretending like I went through the, you might have missed that part. I said, let's pretend that I had like 5 vectors, and I did basically what I did with vector A here. I found the X component and the Y components and their signs and all that. And I had that for 5 different vectors. And then I added all the X components of those 5 vectors together and got, lo and behold, 28 newtons. And I also did all the Y components for all 5 of those vectors and added them together and got negative 32 newtons. So I just pretended that happened. It didn't really happen. And I just took numbers that I wanted to use.
Okay, so but what I guess what I'm saying, so when because I was solving at the same time just to go along with what you were doing,
Right.
I actually got 42.5. I don't know if
Actually,
I
that
did the
might
math.
have been-
I don't know if I missed the math or if I just
Nope,
missed
you're
adding
right.
something.
You actually did it right. Notice mine's a typo. So yeah, you did exactly right. Let's
Okay, I just want to make sure I wasn't missing a calculation somewhere. And
nope, you did it
messed
right.
up.
I had a typo.
Okay,
I'm going to correct this in the notes.
yeah, because I have a tendency to look over things, and I just want to make sure I didn't miss another number somewhere.
No, that's good. Anytime you catch that in real time, definitely let me know too. But if you don't, that's okay. As long as you let me know eventually, that helps. I just literally copied that wrong.
Gotcha. Okay.
Anyone else? I see Jamie sticking around. I'm assuming it's because she wants to see that problem work, and that's cool. I just want to make sure anybody else that might have problems has questions, and let Jamie know I'm here, getting ready to help her.
Yeah, I don't know about anybody else, but I found one of those little answer solution guide things for that
For that
problem.
problem. Uh-huh.
And I read it several times, and all I could come up with is, where are you getting these numbers?
Yeah, so that can be a problem. And in fact, usually when you find the solutions online, they're written for instructors, so it's a little harder to understand. Let me go ahead and answer your question now. So our scenario was 200 milliseconds is what it took to pass a 2 meter high window. So I'm going to draw a little better now. I'm going to say a ball was dropped from here, which is a height h, above a window. And then the window, of course, had a y equal to 2.00 meters like this. And that is from here to here. And we said it took delta t window equal to 200 times 10 to the negative third seconds, like that. Okay. Now I remembered what I think I was looking for. I can call the velocity that the ball has here as v1. I can call the velocity that the ball has here is v0 is 0. And then I can say the velocity that the ball has here is v2. And I know that for constant acceleration, which is what free fall motion is, v average is equal to v1 plus v2 plus v2 over 2. But I also know v average is x minus x0 over delta t. So I can say combine these two, and I'd get 2.0 meters divided by 200 times 10 to the negative 3 seconds is equal to v1 plus v2 over 2. So this becomes v1 plus v2 is equal to, if I do 2 times 10 to the third, that gives me 2,000. Then I divide that by 200 and I get 10. So this is going to be 20 meters per second once I multiply it by 2. So that's a number that I have that relates v1 and v2. Now, what I also know is that v1 is equal to G times, let's call it T1, which is the time required for it to get here. And I also know that V2 is equal to V1 plus G times what I call delta T. Okay. So I can now say V2 is equal to G T1 plus G delta T, which is G times T1 plus delta T. What I'm saying T1 is the time required for the ball to get to the top of the window. Hopefully I'm not going to use that, right? So now I can say V1, which is equal to GT1 plus VT, which is GT1 plus delta T, is equal to 20 meters per second. And I can see that GT1 plus, or 2GT1 plus G delta T is equal to 20 meters per second. Now I know G delta T, so I can say 2GT1 plus 9.80 meters per second times 200 times 10 to the negative third seconds is equal to 20 meters per second. So now I can do some math. I can say 9.8 times 200 e to the negative 3 is going to give me 1.96. When I pull it to the right, that's going to be subtracted from. So 20 minus 1.96, I get 2GT1 is equal to 20 meters per second minus 1.96 meters per second. So I get 2 times 9.80 times T1 is equal to 18.04 meters per second. So T1, which I don't really need, but it's going to help me figure out what's going on with the height. So T1 is going to be 18.04 seconds divided by 2 times 9.8. So I say divided by parentheses 2 times 9.8. So 2T1 equals 18.0, or T1 is equal to 8.04 meters per second divided by 2 times 9.80 meters per second. So you see that's all going to happen is the meters per second cancel out, just leaves me with a second on top, and I get 0.9204 seconds. And that's the time required for it to go the distance h. So I know that h is equal to 1/2 of 9.80 meters per second times 0.9204 seconds squared. So I can now find out h. So I'm just going to take and square that 0.9204, multiply that by 9.8, and then multiply that by 0.5. And that gives me 4.15 meters is what h should be. Now that was a somewhat convoluted way, but this is what I was talking to you about when I talked to you Saturday, Jamie. This is a scenario where we didn't have an equation for the answer. We, in fact, had to use several different equations, and in a couple of cases, we used different equations multiple times. Now, there's probably an easier way, but that trick that I found with the V1 plus V2 over 2 working, that was just a way I happened to have found. There might, in fact, be a quicker way. I could probably think of a couple. I know the way that I was doing before would work. It just was going to be a nightmare doing all the algebra. So anyways, that's basically what it should be. It should have been about 4.2 meters above the window was where the ball was dropped from. So any questions on that?
I mean, yeah, but I'm still way behind where you are, so.
Gotcha. Well, all I'm using in that where I said V1 is equal to GT, I'm using the equation right here. Let me write A is equal to V minus V0 over T. So what that tells me is V is equal to V0 plus AT. So that's exactly what that equation is, because the initial velocity was 0. But it's also what that equation is. So that's where that came from. I already had a relationship between V1 and V2 that when you add them, you get a certain number. So I could actually use this version of V1, this version of V2, and that I would only have one variable that I didn't know in it, and that was T1. So by putting it this way, I was able to eliminate that T1. And once I got that T1, then I could just use a typical, this equation right here is essentially X equals 1/2 AT squared plus V0T plus X0. Only in this case, it was Y equals 1/2 GT squared plus V0Y times T plus Y0. But V0 and Y0 were both 0. So that's why I didn't have all that junk. Does that help you a little bit more?
No,
Well, that's not good.
no, you're going entirely too fast for me to keep up. I'm trying, but
Okay.
I'm trying to actually do the problem as you talk about it, because otherwise it makes no sense. And that's why I'm still
Gotcha.
right at the point where I'm substituting the equations in for the V1 and V2.
Okay. Were you able to get up to the V1 plus V2 equals 20?
Yes, and now I'm substituting the equations for V1 and V2 in.
Okay, gotcha. So I was mainly just trying to explain where those equations come from, because they might have looked like Greek to you because,
No, I already figured that out.
okay, good.
Okay, now I see where the information's, well, for T1 and T, I'm gonna have to figure it out, but
Okay. Were you able to reach that second underlined red equation, or underlined with red equation?
thereabouts.
Okay.
And T1, is that the like starting like 0, or is
No,
that?
that's the time from you drop it till it gets to the top of that window. It wasn't anything that was given to us, but because the initial velocity is 0, that was one I knew that I could come up with pretty easily.
Okay, so T1 would be 0.
No. T1, it turns out to be 0.9204 seconds. Is basically how long it takes the ball to get from the ceiling, or excuse me, from where it was dropped to the top of the window. That's what T1 is. Jonathan,
Okay,
you got something there, Jamie?
Oh, I was gonna say, I theoretically have enough of this set up to be able to get to the right answer, so.
Yeah, and also if you remember at the end of the video, which should be about an hour and 25 minutes in, you can just fast forward to the hour and 25-minute mark, and you can take my explanation, pause it, look at your work, take my explanation again, pause it, look at your work, and that might actually help you do it as well. So you don't actually have to watch the whole video when it comes up. You could just watch that last part if you need some more help. But were you able to get verify any of the equations that I put down there? I mean, I know you got V1 plus V2 equals 20, and then you substituted V1's G times T1, and V2 is equal to V1 plus G times delta T. I think you were able to do all that. So did you get that GT1 plus G parentheses T1 plus delta T close parentheses equals 20?
What? I'm sorry. I'm sorry. I don't understand equations when people speak them. It's too confusing.
Okay, gotcha. Then there's not much I can do. Were you able to get the equation that is underlined on the left-hand side there? Were you able to get something to look like that?
Yes, I'm currently at 1.96 equals 19.6 T.
Okay, excellent. Good job. So now all you have to do is divide. Well, you got 1.96. Well, you should have 20 minus 1.96 equals 19.6 T.
That is true.
Okay, you did get that then?
Yeah, I just forgot to carry the 20.
Okay, gotcha. Yeah, no problem. So that should give you this equation right here once you subtract the 1.96 from the 20. And this is what you said was 19.6 T1. So all you got to do is divide 18.04 by T1, or excuse me, 18.04 by 19.6, and that should give you T1.
Yeah, I've gotten to that point.
Okay, so you're now up to this point. That's awesome. Now all you have to do is notice the red equation at the bottom of this page. That is our typical kinematic equation that I got from the second integral when I was deriving it for you. Only we have the special circumstance where the initial velocity in the y direction was 0, and the initial position we could call 0. And what I'm saying is it's going to go a distance h in a time of 0.9204. So all I have is 1/2 times 9.8 times parentheses 0.9204 squared. So now that you have the 0.9204, I think you can easily get the h part, which is what we were asked for.
I mean, I got in the 4 area, but I have to check my calculator for a moment.
Jonathan, do you have a question while she's working through that? Anything I can help you with, or are you just trying to pay attention so you can figure this out yourself? You might not even be here. Yeah, looks like you might not be. Yes,
Oh, wait, that last part has to be squared.
there you go.
Okay, I got it.
There you go.
So
What you're
now
doing
that
is right.
makes,
You're not willing to trust what's being written down. That's great. That's an excellent thing to have. It's just, until you get quote unquote faster at putting things in and get an ability to hear equations and understand what's being said, it's just going to make it a little slower on you. But you're doing everything right. The stuff you talked about with me on Saturday seemed consistent with that as well. So don't get too discouraged. It looks like you're doing better than you think.
oh, I know that. I just don't like when I don't understand things.
Yeah, I get you.
And unfortunately, I can't really start learning how to hear equations when people give me that much information, especially if there's numbers and variables involved. My
I
brain
get you.
automatically just drops it, which
I
is
get
why
you.
I write things down.
Yeah, no problem.
But thank you. That is very helpful.
No problem. Hope I clarified it for you anyways. Like I said, it's not easy to explain this stuff. It's not easy to understand the stuff when it's being explained, and God forbid if there's a time crunch, it really gets bad. So anything else before I let you
Yeah,
go?
the equations were helpful. Thank you. You have a great day.
No problem. You too, Jamie. Have a good one.
Oh, but the other people stopped questions, so.
Yeah, I don't think Jonathan's here anymore. I asked him, so.
Oh, you didn't, okay, yeah, he sent you a chat, a
Oh, did it?
message.
Gotcha. Thank you.
His computer doesn't have a microphone. I'm sorry.
Oh,
I
okay,
wasn't able
gotcha. Yeah,
to-
there it is.
So yeah, he's still here. He's just not able to communicate through non-chat methods.
Gotcha. I see you, Jonathan. Sorry about that, bud.
You both have a great day.
Yeah, you too.
And thank you for your patience.
No problem. Have a good day. I'm going to share my screen with you and show you the web page I'm looking at. Okay, so these things right here, they have that logo right there, Shalm's Outlines. They make them for like every course. Okay, they're really awesome. But what I'm looking for you, or what I'm suggesting for you, is you look for Shalm's Outlines physics. And they have several of them. Your course that you're taking is Physics for Scientists and Engineers, which, look at this used. You can get this for $4.59. That is 768 solved problems, and it's pretty good. But to be honest with you, it's not as good as the one that you have for the college physics that I see down here. But the college physics one doesn't cover calculus stuff. So yeah, I would say if you had to buy one, I would buy this Physics for Scientists and Engineers. But if you manage to find two new ones at $4.59 and $4.29, I would say buy the college physics one and the Physics for Scientists and Engineers one. There's also one that's basic physics. That's a great one. And there's also one that's called, I think, just physics, and it has like 3,000 solved problems. The more solved problems you can see, the more pseudo experience you can get. And that pseudo experience hopefully gives you the creativity to come up with ways to solve other problems. So applied physics is another one. I wouldn't waste my time on that one. It's good, but it's just not appropriate level for this course. And when you look at them, by the way, like if I click on this, it'll show you down at the bottom what courses it's good for. You can't read it right here, but it says it in this thing. Let's see if I can do it this way. It's still not very big. It says physics for engineers, technical physics, something in physics. But anyways, these little check marks, if you actually maybe go to the site, they'll tell you what courses they're best for. But that is a good option. And for instance, I was an undergraduate and a graduate student, and I still managed to accumulate about 40 of these. So I would say it's highly worth your time if you can afford it to do it. Not only that, I sometimes put them on reserve at the library. I haven't done it yet this semester, but I'm probably going to soon. So hopefully that'll help you. I'm looking at your comment. Yeah, so those Shalm's Outlines, they have basically a chapter that sort of represents every chapter that any level textbook like this Giancoli one is, but it's condensed down to a page or two at the most, and it's just a couple paragraphs.
And then they have a series of examples, some of which are the derivations that a typical textbook would do in them, but other ones are actually examples and they're worked out in detail. So you end up getting, say, maybe 50 problems or so worked out in detail per chapter. And then it gives you like another 20 or 30 problems where it just gives you the answer. And then it goes to the next chapter and repeat and stuff like that. So yeah, if you're looking for more examples of problems, I would do that. They have one for statics. If you're going into engineering, they have one for dynamics. I think it might be called engineering mechanics when it has statics and dynamics both. There's one for strength of materials. They've got them for programming in C. They got them for French vocabulary, all that good stuff. All your math classes, they got them for calculus. They got them for tensor calculus. They got them for vector calculus, linear algebra, all those different courses that you're probably going to take, probability and statistics. So that's what I'd recommend for you. Any other questions? I'm now reading your chat, so that so if you send me a chat, I'll get you. You're welcome. I'm going to go ahead and split then. I hope you have a good weekend. Take care and see you next week.